Hey, it's Kyle back to talk about part 3 of our homework. And in part 3, we're going to be creating a function that calculates a surface point that is a specific radius away from our central helix that we made. And it does this at any t and any theta along our helix. When I say theta, we're going to be defining this surface equation in the axes of this n vector and b vector. So as we talked about in the last part, we have our normal vector, our tangent vector, and the binormal vector around our helix. We calculated, we made a function that can calculate the normal vector and the tangent vector, and the binormal vector is just the cross product of those two vectors. Why it's important for us to have this cross product is that our normal vector and this binormal vector create a plane that is like perpendicular to the helix that we have at all points. And in this plane, we can then create a circle that goes around our helix at a radius we specify, which we want to do 0.5. So if you look at this picture, it can kind of help see it. This n and the b almost create a set of axes where we can plot around our helix. So that's what we'll be taking a look at. And since last time, I went back and modified my last functions so I don't have to feed in a t, an r, and an mz every time. I can just feed in t. And that can be helpful just to simplify things. So what we want to do for that is we want to make it so we can only feed in t when we want to call on the tangent or the normal vector as well. So I'll make tangent normal, and I'll call on my function. But this time when I call my function, I want to use a partial lambda function. So this is just saying, like I want to be able to use any t, but I want to have my r and mz hard-coded outside of my function. So r equals r and mz equals mz that I have predefined. And now we can kind of get into actually making the surface function. So I'll define a function surf. And this function takes in t and theta, as we discussed, and I don't have to feed it r and mz since I'm like hard coding those outside. So now, or I guess I can kind of show that for a second. So basically now, if I want to find a tangent at a point, instead of giving it like 0, mz like I did earlier, I can just give it 0, and I can get the tangent at a point t equals 0, or if I want to do 2 pi j and p dot pi times 2, I can do the same thing. So it's just a lot easier. Alright, so now back to this function. So now I've defined the function, and I need the tangent vector. So we'll say t, and we'll say it's equal to tan at the ti set, then n is equal to norm at the ti input. And as I mentioned, we have this binormal vector that is just equal to the cross product, so j and p dot cross of t and n of our tangent and our normal. And I didn't mean to run that, but it's fine. And now we want to actually kind of create the circle in our n and b axes. So it's going to end up being the thing we want to return from this function. So we want to make our axes, so the first thing we'll do is j and p dot stack. We want to stack n and b as essentially as our x and y axes that we're going to use. want to do a matrix matrix multiplication with the matrix that we want to use to draw our circle in those axes. So that is going to be a matrix of the radius we want, and then the theta we feed the function, and need to do JNP dot cosine. And then same thing for the y, which will be r times JNP dot sine the theta we feed, and this should be good. So now let's say I call on surf at 0 and, well, we'll just say 0, 0. It's not defined. Okay, I called it tangent, and I called it norm. Alright, so this gives us our point, and it says it should be at x of negative 0.5, 0, and 0, but clearly if we take a look at that, that would be a point right here, and that is not a radius of 0.5 away from our helix, and this is because we didn't actually take into account the helix that we created earlier. So we want to do basically the distance away from our curve that we made. So we still have to include in the curve at t, r, and mz, and we add this to it. And now we can clearly see at a surface point of 0, at 0, 0 for t and theta, the point in our surface that we're making would be 2.5, 0, 0, which looks a lot better, as it'll be around here, which is around like a half in from our starting point, and then 0, 0y and 0, z, which is where we want it to be. And then we can kind of check this out at other points. So if we keep it at 0, t, it'll still be around that first point of the helix. But if we want to see where it's going to be at like 90 degrees later in the circle, we can do jnp dot pi divided by 2. And this is going to be at above our point on the helix, so 3.5 in z, and then it goes a little negative in y, and that's because the circle goes around our point as our helix is going upwards, so the circle actually tilts a little upwards and starts to travel along the path of the helix. So looking good, and next will be part 4, where we actually create the pipe that travels along the whole helix. So thank you.